Okay, this is Algebra 2 notes. We're working on section 8.4 in our book on infinite geometric series. Yesterday in class, we looked at an exploration of which infinite geometric series have a sum and which ones don't. So our core concept is that the sum of an infinite geometric series with the first term of A1 and a common ratio of R is given by the rule S equals A divided by 1 minus R. And that is going to be true as long as our common ratio, the absolute value of our common ratio, is less than 1. So we're talking about values for R like 1/2, -1/2, 2/3, and so on. If the absolute value of our common ratio R is greater than or equal to 1, then the series has no sum. So let's do a couple of examples of finding the sum of an infinite geometric series. In example 1, number A, we want to find the sum of the series from I equal 1 to infinity of 3 times 0.7 to the I minus 1. We do know that it's geometric. It's of the form A1 times R to the n minus 1. So substituting in 1 for I is going to give us our A1. And in this form, when it's I minus 1, 1 minus 1, that's to our 0 power. So A1 is 3 times 0.7 to the 0, or just 3. Our R is easy to spot. It's the base of the exponential part, so our R is 0.7. And that is indeed between -1 and 1. The absolute value of 0.7 is less than 1. So we have a sum. So let's use our formula. Our sum is equal to our first term, which is 3, over 1 minus 0.7. So 3 divided by 0.3, or 10. Our sum is 10. Okay? Now let's look at our next example. It's written in a different form. It's a sum. It's an infinite sum. As we go from 1 to 3, it's multiplied by 3. 3 to 9 is multiplied by 3. Each time we're multiplying by 3. So our R here is 3. And since R is greater than 1, 3 is greater than 1, we have no sum. Yeah. Let's look at our next example. Again, it's written out as individual terms added together. And as I look at our values here, our ratio between terms, -3/4 divided by 1 is -3/4. So is that what we multiply to get to each term? As we go from -3/4 to positive 9/16, yes. If I multiply by -3, I get positive 9 over 16. And again, if I multiply by -3/4, I get -27 over 64. So this is our value of R. The absolute value of that is less than 1, so we have a sum. We just need our A1. Our A1 is our first term here, so our A1 is 1. So our sum is A1 divided by 1 minus -3/4. So we have 1 over, or divided by, 1 plus 3/4, which is 7/4, and that equals 4/7. Divide by 7/4 by multiplying by the reciprocal. Okay, so those are example 1. Let's look at a couple more examples. Here we have a word problem. Here's example 2. We have a pendulum. It's released to swing freely 18 inches on the first swing. So right here we release our pendulum and it goes 18 inches. On each successive swing, the pendulum travels 80% of the distance of the previous swing. So when it's coming back, it only goes 80% of 18. And again, the next swing, 80% of that, and so on. We want to know the total distance. Well, first off, this is a geometric series. It's geometric. Our R between swings is 0.8. Each time I go from one term to the next, I multiply once more by 0.8. And our A1 is our first swing of 18. It has a sum because 0.8 absolute value is less than 1, so we know that it has a sum. Our sum then is A1 of 18 over 1 minus R. So I have 18 divided by 0.2, so we end up with 90. Moving our decimals over, 180 divided by 2 is 90. So the total swings that the pendulum goes as it goes less and less each time is 90 inches. Okay. An interesting application of geometric series, infinite geometric series, is that of with a repeating decimal. We could write a repeating decimal as an infinite series by just looking at the place value. As I look at this, our 0.242424, and it continues in this pattern. The first group of repeating digits right here can be written as 24 over 100 because this is in our hundredths place. Our next one takes us tenths, hundredths, thousandths. This is in our 10,000ths place. So we're going to add 24 over 10,000. Our next pair, 10,000, 100,000, and 1 million. So 24 over 1 million. And it would continue just like this. Okay, dot, dot, dot. So as I go from one term to the next, my ratio is 1 over 100. Our A1, our starting term, is 24 over 100. So let's see what our sum gets us. Start with A1, which is 24 over 100, divided by 1 minus R. Well, 1 minus 100 is 99 over 100. So I have 24 over 100 divided by 99 over 100. Well, to divide with fractions, we flip and multiply, so this becomes 24 over 100 times 100 over 99. The 100s reduce, and I can also reduce by 3 in the numerator and denominator. So reducing by 3 gives us 8 and 33. This is the fraction 8 over 33. Okay, what does that have to do with a repeating decimal? Well, let's try it the other way around. If I take the decimal 8 divided by 33, I get 0.24. Okay, so what we see then is we can take, using it as an infinite geometric series, we can take a repeating decimal and rewrite it as the fraction. Okay, let's try another one of those. This one's slightly different because we have a 0.1, we have a digit before the repeating part. So as we look at that, our first term here, 0.1, is the fraction 1/10. And now our repeating part is only one place value. This 6 is in the hundredths place, so we're going to add 6 hundredths. And then the next 6 is in the thousandths place, so 6 thousandths. And then in the 10,000ths place, and so on, as we keep going. This part forms an infinite geometric sum. So I'm going to find this sum, and then I'm going to add on the 1/10. So my total value is going to be 1/10 plus whatever this sum is. So let's see if we can figure out what the sum is. My first term in the geometric series is 6 over 100. The ratio between terms this time is just 1/10. 6 100ths times 1/10 is 6 over 1,000, and so on. So our sum for the geometric portion is A1, which is 6 over 100, divided by 1 minus R, which is 1 minus 1/10. So I have 6 over 100 divided by 9/10. Flip and multiply. We get 6 over 100 times 10 over 9. Let's do a little reducing with that. reducing by 10, and reducing by 3. So we end up with, well, we have 2 over 30, but I think we can do a little bit more reducing. We end up with 1 over 15. Okay, that's our infinite geometric series part. Now let's finish with the fraction. Our fraction, we need to add 1/10 plus s. So 1/10 plus 1/15. I guess I should have left that as 30ths. This is 2/30ths, and 3/30ths is 5/30ths, which reduces to 1/6. So our infinite geometric sum here, our decimal 0.01666666, is equal to 1/6. And that's our video.